Good. But this is such an amazing audience. As I will tell you in a second, super not in sort of like astrophysics or sort of this specific field, but hopefully some of the ideas that I'll present today extend. But today I'm going to be talking about sort of this idea of, are all AI models the same? And we'll be talking about a adaptation of a Platonic representation hypothesis, the strong Platonic representation hypothesis, imaginatively named. And this is joint work with Colin Jang, my advisor Vitaly Shmatikov, and Jack Morris out of Cornell Tech. So thank you for the introduction, but a little more on me is I'm a third-year PhD student out at Cornell Tech, and as of 2 weeks ago, I Google Research as well. I worked with Vitaly Shmatikov on machine learning safety. I put safety in quotes because I think that can mean a lot of different things to a lot of different people. And primarily sort of the objects of safety that we're interested in are embeddings, agents, and multimodal LLMs. And before Cornell Tech, before Google Research, I was at Microsoft and the University of Washington. And to translate that last slide, I'm neither an astronomer nor a physicist, but I hope sort of these ideas extend and are helpful to people in this room. So I'm going to recipe to translate between AI models' internal representations by harnessing their sort of surprising geometric similarity. And I think people in this room might be familiar with the Platonic representation hypothesis. I think there was like
let's not assume it.
Okay, we won't assume it, but for those who are familiar, this is trying to harness that representation into actually doing something interesting with it. I'm going to introduce it from an angle that I do know, which is security, but hopefully with some time, we'll be able to tie it all together into something that's useful. So a bit of a game plan. We're going to start off with a bit of background on embeddings. And then we're going to go in a brief aside and sort of how we ended up at the problem that we did. So this is thinking about how much information embeddings delete. And then we're going to bring that all together with vec2vec, which is a framework to translate embeddings from one space to another, from one model to another. And yeah, let's get into it. So this might be a review for some of you, but I just want to make sure everyone's at the same spot. Just a bit of background in embeddings. When most people think of language models, they think of a ChatGPT, they think of Claude, but they think of text-to-text models mainly. That being said, despite emitting text, language models often operate on vector representations that I'm going to call embeddings. And language model weights, as many people know, or at least in the foundation model setting, are usually trained with data from the entire internet. And what that effectively does is it imbues these vector representations, these embeddings, with really strong semantic priors. And these semantic priors are what we're going to be trying to grasp with. This is what the universal geometry comes out of. Language models that just emit embeddings, we're going to call encoders. So you're going to hear me use the word embedder, encoder, and model all interchangeably. And semantic priors plus some post-training are what actually make encoders useful in practice. One thing that encoders are very useful for is search. So in this picture at the side here, we have a vector representation or like a 2D representation of every article in Wikipedia compressed down to 2 dimensions after being embedded by an embedder called GTE. And just to walk through the search flow very quickly, each one of these points represents a document. And when you run search, you ask a question perhaps, and that question is then embedded using the LLM. And we're going to find the nearest vector to that question. That's going to be our response. That's what we asked. And one question that we asked is sort of, why are embeddings so useful for search? And I think a good place to start is with the predecessor to the encoders that I just mentioned a second ago, which is word embeddings. Semantically related words, so horrible and terrible in English, map to numerically similar vectors. Whereas horrible and perfect and schlag, whatever that means, probably not aligned, right? Modern encoders, especially the ones that we've been thinking about, generalize this notion to not just words, but whole documents and different modalities. And the key thing that I sort of want to take away from this background section is that closeness is a property of the inputs, right? So this sound of a dog barking, for example, and a picture of the dog itself, those are close in semantic space. These aren't close in relation to any one model. right? And importantly, that closeness, as I mentioned a second ago, is regardless of the encoder and regardless of the modality. So two inputs that are close in one model should be close in any model. And that's sort of the idea that we're going to play around with for the rest of the talk. So just a quick, more background embeddings, useful for search, useful for summarization, useful for RAG for people who are interested in that. Tons of companies are thinking about embeddings. Tons of money is being poured into embeddings, which for me, a security researcher, makes it a pretty prime target for attack. And that sort of led us into this question of how much information do embeddings actually leave? And this is a quick security aside that I hopefully will be able to drag back into stuff that might be useful for this room. So very quickly, I think the question that we asked was, what can a bad actor learn from just looking at embeddings? So say you have a hospital and the hospital embeds a bunch of patient records. If an attacker were to leak that database, for example, what could they actually learn? Some challenges in going from vector back to text is that if you're to change the input text with even one word, you get dramatically different vectors, right? So the sentence Rishi is standing behind this podium and Rishi is standing, these embed to different vectors in numerical space. The second is the data processing inequality, which is an information theoretic concept saying that any operation you do on an input must at least lower sort of the amount of information in the output, right? So if you embed text, you must at least lose information. Maybe you can keep the information constant, but you can't gain information. This means that going from a vector representation back into text, you've maybe lost something, and that makes it hard to invert from vector back to text. Right? And to quickly answer the question, embeddings leak almost everything. This is some work from a co-author, Jack Morris, and they released a paper, text embeddings reveal almost as much as text. And the key idea, not really important in this talk, but if people are interested, is essentially a smart search, which relies on repeatedly querying the encoder until you generate a hypothesis text that's close to the output text. It's essentially smart search. But the key part of this is that it relies on an encoder, right? And again, the key idea, encoders imbue a ton of semantic information. And in the special case where we have access to the encoder, we can actually invert vector embedding into text, right? One question that will lead us into vector is, what if we don't actually have access to the original encoder? We just find a bunch of embeddings lying on the floor. The question then is, do embeddings still contain enough information that we can extract information from, right? And that leads us into our framework, vector. And the setting here is, you find this lying on the floor. For most of us, that's pretty interpretable. I mean, if you can read that, props to you. And the idea is like, okay, I found these vector embeddings lying on the floor. What can I actually learn from this, right? Like, what can I actually do with this? And my advisor made me put this in, but if anyone's seen the movie Arrival with an alien language, his sort of analogy is that without knowing the encoder, vectors are seemingly meaningless, which is the same as trying to understand some sort of alien language without access to the aliens themselves, right? And the question then is like, what do you actually do? You know, like, you might be like, Rishi, you're insane. Like, you just found these numbers, this matrix on the ground. What are you actually going to do with it, right? And the hope is this, to do some sort of unsupervised embedding translation. And I think this is where we're going to start to tie into stuff that might be relevant to this room. And the idea is that we're going to translate these leaked vectors, these vectors we just found on the ground. Those are all in red. We're going to translate it to a known space in purple, right? And then we're going to run analysis in purple. If you remember from a second ago, vector text says that if you have access to the encoder and you have access to the embeddings within a space, you can run some analysis there, right? We can draw out text from embeddings with access to the encoder. We don't. Go ahead.
Oh, sorry, I should use this. Yeah. So this known space is something that you've encoded yourself, presumably. So you have access to an encoder, but does it have to be? You have to assume that it's been encoded on the same original data as your space.
Really good question. We assume not. And actually, you beat me to it. That's my next one. Importantly, we do not have access to the documents. Right? We don't know what documents the source and source embeddings come from. These can come from any, right? We don't have access to this encoder. We don't know what M1 was. We don't know what DI is. And importantly, we don't have access to matches VI in sort of the purple space. So say UI was generated from an email, say from Enron, and we want to translate and recover F of UI as close to VI as possible. But we do not have supervision here. We don't have a supervised pair on the other side. Again, we just have these leaked embeddings on the floor. We don't know where they came from. So hopefully the task itself makes sense. And the high level hope is that we can use the semantic structure that I mentioned a second ago. So when I was doing the intro on embeddings, the high level hope is that we can use that same semantic structure to generate sort of a Rosetta Stone between the red space and the purple space, right? To put that in a picture, recall that for any encoder to be useful, two semantically related inputs must encode into similar vectors, right? If I'm running search over a database, my query better encode into a similar place as my answers, right? And this is a property of content, not a property of encoder. And I think nobody sums up sort of this view, this worldview better than some folks down the street at MIT. They published a paper called the Platonic Representation Hypothesis. Their words are better than mine, so I'm just going to read straight off the slide. But they say that neural networks trained with different objectives on different data and modalities, we'll get back to modalities in a second, are converging to a shared statistical model of reality in their representation spaces. For us, what that means is if the PRH is right, if the Platonic Representation Hypothesis is right, there should be some sort of shared statistical model of reality in between red space and purple space, right? And the hope then is that not only one, can we characterize this space, this like universal representation in between red and purple space, but also we can translate to that space and back from that space. In a way, we're doing model-to-model translation in the internal representation space. That's the goal. Uh-huh.
Now, are you assuming that you know something about the data that the first space was trained on? Because I can imagine you know the whole embedding of everything, and then it should look similar for every model. But then this might be just a little tiny part of one, and how are you going to identify that?
Yeah, it's a great question. So for our experiments, well-formed English medical text on one side and English on the other, our method starts to break down, but I don't think that's a function of the Platonic Representation Hypothesis. I think it's because I'm bad at ML. I think there's sort of like other reasons things fail there. But for example, if you have Wikipedia articles on one side and tweets on the other side, these are like tweets you could say arguably not well-structured English, but these are like very different samples of English. But you can still translate from red space Wikipedia articles and purple space tweets. So if you if you're trying to, like the leaked embeddings on the ground were a bunch of tweets, and you only have Wikipedia articles, you can actually extract information from that. I'll get more into that in a second, but that's a great question. So how we actually do this, for people in the room who know what CycleGAN is, we use something very similar to CycleGAN, but we make a bunch of changes. If you don't know what this is, don't worry about it. Not that important. Our approach we call vector-vec, imaginatively. And I don't expect you guys to read the whole picture, but recall that the settings that I found this red embedding set just leaked on the ground, just found it like walking around. Unknown encoder, unknown documents. But I also have access to a known encoder and known unmatched documents. So this goes back to your question, I think. So the documents D that generate this red embeddings, in this case, are a bunch of Enron emails, right? Whereas the documents W that we have access to are a bunch of Wikipedia articles. What we show is that this is actually enough to learn a translation between red and purple and extract information from red. Some details. The idea is that we're trying to learn sort of a shared representation space L between the red set and the purple set. This is the like sort of Platonic space that we're trying to find. Another way to say that same thing is that L is our Rosetta Stone between red and purple. And then architecturally, for those who care, each embedding space has an input adapter A and an output adapter B. So, and importantly, the input adapters are going to share some weights. So when we translate from the red case, what we're going to do is we're going to take the vector in red, we're going to put it through A1, the input adapter for red, through some shared layers T, then through B2 into the purple space. That's translation, right? And A2, the input adapter for purple, and A1, the input adapter for red. Sorry, this diagram is meant for something else, so it's a little scattered. Both share layers T. So when we're translating from purple to red, we're going to go from A2 through T through B1 back into red. That's translation back and forth. As I mentioned a second ago, shared weights T are attempting to ensure that both sets use the same parameters to encode similar semantics. We don't want to waste all these parameters and encode the semantics for cat twice, right? We don't want parameter 1 and parameter 10 to both be referring to cat. We want them to use the same parameters for the same concepts. That's why the shared weights T are important. And for people who care, each component is a residual MLP. If you don't know what that is, it's just a standard neural network. And one of the key losses here is cycle consistency, which is saying that the out and back translation better be the same. So if I were to take a red vector, I'm going to translate it all the way to purple, and I'm going to translate it all the way back. That red vector and the new red vector, we'll call it red prime, those better be very similar to each other, right? If those aren't similar to each other, something's gone wrong in the back and forth translation. And that's one of the main constraints. Yeah.
So how is this different, or what advantage does this approach offer over something like just forcing the alignment between the two vectors with a contrastive loss or something like that? Is there an analogy there that is possible?
Yeah, so the key limitation we have in this space, oops, sorry. So like, if you were to have, oh, sorry, I'm looking for the slide. Yeah, if you were to have a red vector for Rishi standing in front of the screen and a purple vector for Rishi standing in front of the screen, you can do something very much simpler, right? You can say, in latent space, those two things better look the same, right? But we don't have that. So we have to sort of like make do with ourselves, right? So when we do translation, like Rishi standing from the screen, all the way back into the purple space, we have nothing to compare it against, right? So we have to sort of bring it back, which makes our setting a little bit more challenging. One thing that we can do, you keep beating me by one slide actually, is that you can check the distributions. You can do some technique called a GAN, a generative adversarial network, where you essentially are penalizing the distributions of the translations into purple and actual purple. Okay? But that's sort of the best you can do, right? There's no direct comparison, so you can't directly compare how well you're doing. But yeah, did that answer your question?
Yeah, I think I realize you don't have like a ground truth as to which part of your relates to that part.
Right.
Yeah. More one follow up or no.
There's a couple of other constraints. I won't go into them, but I'm happy to talk about them at length later. Yes.
So if I understand correctly, you're saying that impressive learning would be better. So if you had that ground truth, this should be worse than impressive learning, right? Because you have less of a handle.
Yeah. So we're insane. So we went for the worst case possible. With any more knowledge, you can do better. So if you were to have paired data, even just a little bit of paired data, you can do a lot better.
So then you'll have to have the same, you're assuming that no matter how different these domains are, as long as they're text, they do have the same information. They have a lot of shared information.
So yeah, so I think another perspective on that is they can be different distributions of text, but they come from the same source shared semantics. That's the important part. They come from the same Platonic representations. And the hope is that you're learning this sort of universal Platonic structure as opposed to the specifics of what each embedding is doing. That's sort of the hope. An open question is how far apart can you pull these distributions? In some recent work, we're trying to do images on one side, text on the other. Those are pretty far apart. Work in progress. It may not work, so don't quote me on it. But there's other people trying to do different languages. That's something that's been known to work in word embeddings. Other folks are trying to do like chemical models on one side and text models on the other. I'm a little skeptical of that, but maybe. But like, I think it's an open question how far you can pull the distributions. Sorry, did that answer your question?
Yes, thank you.
We might need to wrap it up in the next 5 minutes, so.
Okay, yeah, no problem. But yeah, please keep the questions coming. But yeah, experiments. So we run experiments with 7 different encoders, and they're each trained with like vastly different algorithms and data. Just to walk through this diagram a little bit, very different parameter sizes from 100 million to 4 billion. Different backbones from T5, which was like the first draft out of Google, and then QN, which came out like 2 months ago. It's like a large mixture of experts distilled into a dense model. I read that from the paper. I don't even know what that means, but completely different than sort of the base. It comes from many different years, from 2021 all the way up to 2025. And the dimensionality is very different, right? So 512 dimensions all the way up to 2048 dimensions. So these are the dimensions of the embeddings themselves. Some encoders are multimodal. So CLIP is trained with images and text, whereas none of the other ones have images like anywhere close to them. Granite and QN3 are multilingual. The other ones are monolingual. So main point here is that they're all trained in sort of like vastly different ways. And another way to look at that is numerically the embeddings of different architectures are producing very different vectors. So say you're to embed a whole data set in GTR, and you embed a whole data set, the same data set in Granite, and you compare the embeddings or the matching embeddings at each set, right? In our setting, we don't actually have these matches, but say you were to have them, right? The cosine similarity on average between any 2 paired embeddings is minus 0.02, which means they're essentially perpendicular. There's no, not, right? You get no information. These are the spots that are not dark blue. These come from similar architectures. So GTE, E5, and where's my other one, Stella, are all from BERT architecture. And it turns out sort of the ground truth embeddings of the same text just happen to be somewhat similar for BERT. But cross backbone, definitely not the case. In latent space, however, none of that matters. So the same text, Rishi is standing in front of the screen, embedded in Granite and embedded in Stella. 2 different architectures, 2 different years, completely different training paradigms. In latent space, they're very, very similar to each other. So effectively, VectorVec has found some sort of alignment between these 2 things without having any matching across. And the cosine similarity, I think, is interesting. I think the latent space similarity is interesting, but that doesn't tell the whole picture, right? You can have vectors that are close to each other, but not emitting any semantic properties, right? You can maybe find the mean of all vectors in the target space, and that actually gets you relatively far as cosine similarity goes, right? So one question you might ask me is, what is this actually useful for? And I think circling back to this original question, the translations actually do maintain important and critical semantic information. So to walk through this diagram, the Enron email, as Embedding says, the Enron email. What we're going to do is we're going to embed that. So we're going to take this embedding UI, we're going to translate into VectorVec, and then we're going to run vector text, that thing I mentioned earlier, and run some analysis on the text. If the text that we generate from this translated embedding is even remotely close to the original text, we've gained something from this translation, right? We're maintaining some sort of semantic information. And it turns out it's not perfect, but actually relatively close. Relatively, somewhat. So we maintain mean. I like this one a lot because Enron isn't a word in sort of the target distribution. So we get NRO, N. But we're able to extract names like Enron or close to Enron. We're able to extract names like John. Trades for some future date become future transactions. The following expense report becomes the upcoming expense statement. But we're at least gaining some sort of information from this translation, right? So the translation, without having any paired data, is somehow managing to extract some of the semantics from the source space and transport that into the target space. I should note that these generations are also affected by how good our inverter is, how good vector text is, right? And turns out vector text is not that good at noisy embedding. So some of the noise you see here comes from vector text. And am I running out of time? Okay. Okay. Okay, should I wrap up quickly then? Okay, cool. So you can do other interesting things like stitch additional modalities onto unimodal models. Like if you translate from unimodal model onto CLIP, all of a sudden you can do text image search. And I think at a high level, the idea is that universal representations not only exist, but we can characterize and use them. 1 minute. Cool. And this sort of leads us into the main pitch of our paper, which is the strong Platonic representation hypothesis. That not only does the universal latent structure of text representations exist, but it can be learned and furthermore harnessed to translate representations from one space to another without parallel data or access to the encoders. I'm breezing through this quickly. The original Platonic representation hypothesis mentions this for all modalities. And for people who are paying attention, I only did it for text. We don't think this is a limitation of our method. It's just a limitation of time, really. So we're currently exploring this for more modalities. We conjecture that anywhere that the Platonic representation hypothesis holds, vec2vec should hold as well. For some folks in the room, like this is very relevant, especially in astronomy. It seems like Platonic representation hypothesis holds, so we think vec2vec could be useful here as well. Some future work, and before I end, some aspirational work translating from Whale to English, and alien to English, if you will. And with that, I'd like to give a quick shout out to my collaborators. I shouted them out at the beginning, but Jack, Vitaly, Colin couldn't have done it without them. And eternally indebted to all 3 of them. With that, I'll leave it to questions, but I mean.
I'm afraid we do not have time for more questions, but please reach out if you want to chat more about this. We do have to move to the next story probably. And while the next speaker gets on the floor, I'll introduce Nora Wagner. Is visiting for the University of Vienna. She might be visiting Calvin's group or just Sebastian. Yeah, Sebastian was the one contact. And Nora is Nora. Apologies, are you correct? Yeah, okay, Vienna. Yes, distance. Okay. And Nora is going to tell us about clustered star formation and how to.
Thank you. So thank you for the introduction. Yeah, I'm a first year PhD student. I just started in Vienna, and I'm here to visit my collaborator, Sebastian Ratzenberg. And today I can talk about my current project I'm working on, which has the aim to develop a new clustering algorithm in the nearby Gaia data. So I'm concentrating on the very local area, like on the local 100 parsec sphere. And yeah, we know that stars do not form in isolation, but they form in clusters out of molecular clouds. And over time, they can disperse, but initially they share the same motions and positions in space. So why do we want a new census of star clusters in this nearby region? Because these clusters can help us to reconstruct the recent star formation history. And also these are excellent targets for studying star and planet formation. These stars are very close, so many of them are low mass stars or even brown dwarfs, and are often exoplanetary hosts. So these clusters can be excellent age anchors for those objects. This is a map of the nearby known star clusters compiled from Gagne, Hunt, and Ratzenberg et al. And we can see in this local 100 parsec sphere, which is the region that I'm concentrating on, in the northern hemisphere, it seems that there are no clusters yet found. And some clusters that are known in the southern hemisphere are very poorly constrained in their membership. So I want to investigate, are there more clusters and can we find more memberships, more members of the clusters that we know? So for the measurements of the positions and also of the motions of the stars, we have this Gaia astrometry. This is very precise for almost 2 billion of stars in the Milky Way, but we only have radial velocities for some tens of millions of stars. And these radial velocities are necessary to recover the full 3D motion of the stars. So up to now, the clusters that we have detected yet were found by applying mainly density-based algorithms due to this Gaia data in the astrometry 5D space. And this already led to the discovery of thousands of previously unknown clusters. However, in the immediate solar neighborhood, those are not successful because we have to deal here with projection effects. So when we look at the dispersion and proper motion over the distance for the Gaia objects that we know, they seem to explode below about 112 parsecs. So applying here density-based clustering was not very successful because we cannot detect over-densities in space. Above this threshold, this makes sense. Let's look at this more visually. I have generated 5 clusters that are very dense in the velocity space, but more dispersed in the positions, which is realistic in the real data. And we can see these could be detected with density-based clustering, but over the field stars. But when we look at the observed space, like rect ascension and declination and the tangential motion, these are widely dispersed. So applying here density-based clustering will not return result. So ideally, we want to cluster in this 6D galactic Cartesian frame. But the problem is for the 3D motions, we need radial velocities, and we only have them for about 20% of the stars within 100 parsec. So we come up with the idea of optimal radial velocities, and out of them we can compute the minimal 3D velocity distance of pairs of stars. So the idea is when we look at 2 stars, their velocity difference will be small if they are within the same cluster, and large if they are not. And we can write the difference of those 2 stars in 3D velocity as applying a transformation to the observed data. And when we write this as quadratic difference in their velocities, we get a quadratic function with 2 unknowns, namely the 2 radial velocities of both the stars. And we can find minimum possible value for those 2 radial velocities given their observed 5D astrometry. And when we compute this back with coordinate transformation into the 6D phase space, we can compute a minimal pairwise 3D difference of those stars. And when we compute this for all stars pairwise, we can build a pairwise distance matrix, which is useful to give us an additional constraint on the velocity space, like how close, how dense are these stars in the velocity space. Let's look at this also more visually. When we have like 3 stars that are truly within the same cluster, they move in the same direction. And we have some unrelated stars that move in different directions. And we compute these minimal pairwise distances for each star to each other star and put this into a pairwise distance matrix. Then the star for the first star will have like low values in the difference to its real cluster members and higher ones to the other stars. So we will have here a kind of block matrix with low, around 0-ish numbers, while in the other region there will be high pairwise distance. And yeah, this is this clustering, this matrix that we can use for clustering. The issue is that this does not follow the triangle inequality and therefore does not build a metric space, which density-based clustering needs like HTB scan, because we compute all these radial velocities pairwise. So one star can have different radial velocities depending on to which star we compare it to. And there are density-based clustering algorithms that can be applied to semi-metric spaces, such as the softmax algorithm, but it scales very bad because it has to do the computations with all of those n stars. So it scales with n squared, and we have about 600,000 stars in the local 100 parsecs, so this is very inefficient. So we did two approaches, and I tested them on synthetic data samples onto, this is like a very baseline data sample that the clustering algorithm should be able to recover perfectly. Like we have very dense clusters in the 3D positions and velocities, and also in observed space, they are rather dense in the positions, but already harder to find in the tangential velocities. I got rid of 90% of the radial velocities to get like a true case. And when you would apply HDB scan just in this observed 5D space, you could achieve a maximum NMI of 0.83. And NMI is a normalized neutral information score telling you how good is my clustering. Like 1 would be a perfect clustering and 0 would be we cannot find these clusters. So 0.8 is actually not bad, but for this very simple data sample, it should be work perfectly. And then I have this other data sample that I already showed you before, where we have just large dispersions in the observed data. And if we would apply HDB scan here, we have a maximum NMI of 0.3, which is very, very bad. So the first approach is a deep learning approach with the goal to learn an underlying 6D latent space where we can cluster in, where we can find these clusters as overdensity over the field stars again from the 5D input in
That's me.
yeah.
It's not the time, it's not the time. I'm still doing fine. Sorry, that was a funny noise.
Very good. So yeah, we have an encoder that learns from the 5D astrometry, the 6D latent vector. And from this 6D latent vector, we go back with an analytic decoder. This is just coordinate transformation, but implemented in a differentiable way. Back to the 6D observed space, like this with the radial velocities that we now have predicted. So when we look at the architecture, I have as input data, like all the stars and their astrometry, but for radial velocities, I only have the measurements for those 10% of stars that have radial velocities. And then I split it up in several batches, so small sets of this data, which makes it more computationally efficient. And then I put it into an autoencoder. I learn this 6D embedding, and then I have this analytic coordinate transformation basically back. So this is a semi-analytic autoencoder, and I have here the 6D reconstructed data. So
Those are 6D data as an input.
the input is also 6D, but only contains radial velocities for some stars. And the learned is like the 6D for all stars, and this is also, we have like radial velocity estimates for all stars. Yeah, sorry.
Is it a concern that the embedding vector the same dimensionality as the input vector, so there's no bottleneck in the autoencoder? Or does the upper loss make up for this?
Like, actually, it's not like the input, we tested like different dimensions. We had like also that we put into it, like, for example, the XYZ values that we know and these UVW values that we can compute for some of the stars. But for this, like the input is actually, like it's a 5D input, and we put, we have this information only for those some stars.
Okay.
If this makes sense.
Yeah.
But it's not really, yeah, like it's kind of from 5D, but we just learn with this additional information too in the last function.
Okay.
But the dimension is 5D. Okay, and exactly, yeah. How do we like invent this information that we don't have? We learn to minimize the loss function that depends on different terms. We have like a reconstruction loss term that tries to reconstruct the reconstructed 60 observables to the input of this edge. And then we have an additional loss term for the radial velocities that tries to minimize the difference in the distributions. I will go into the losses more deeply in the next slide. But we also have like a matrix loss term that wants to get a correlation between the optimal pairwise distances and the Euclidean pairwise distances of the latent space. And once the model converged, we apply HDB scan to the learned UVW values and the true XYZ values that we have from coordinate transformation, and then we can get a clustering result. So the loss function that we try to reduce is looks like this. We have these three terms, and the beta values are like the hyperparameters in this architecture. And yeah, the first one is just like trying to minimize the mean squared error of the observed 6D observables with this radial velocities that we have, and at the predicted complete observed, like the complete predicted observables. And then I have like a second loss term that tries to minimize the distribution of the learned radial velocities of the batch to the some true radial velocities that we have. And yeah, rightly. And then I have a third loss term that looks at this semi-metric distance from the beginning, that's optimal 3D velocity distances, and looks also at the pairwise distances in this predicted latent space. And it orders in each row the entries for each stars in an ascending order. So we have very small values on the left-hand side. And we can, when you look at the values up to a certain value, like we take distance, like maybe the 10th, and take then the mean, we get a value that tells us, is this star maybe in a cluster or not? If it's like a low number, it might be rather in a cluster. If it's a large number, it will not be in a cluster. And then we compute the same for the Euclidean pairwise distance matrix, and we want a Pearson correlation to maximize here. And when we look at the predicted latent space that I learned from this, compared to the true 6D latent space, we can see we can find overdensities over the field stars and can apply here HDB scan and find again the clusters. So it's not the goal here to predict this 6D space perfectly, but to find a space where we can cluster in and find these clusters again. And when I look at the more challenging data sample, we see the 3D velocities that we learned are not perfectly, but still we can somehow, with HDB scan, get them as overdensities. So when we apply here HDB scan in this learned space, we can find all the 5 clusters with an NMI of 0.74, which is not like a perfect, but we can find the dense cores of them. And what's good is about that we also, it's very robust. So I tested various hyperparameters, and for all we get similar results. And we also have a noise removal from this HDB scan. And we can reduce the memory from like n squared to m squared, which is the batch size. It's much smaller than the total number of stars. However, the runtime is still large, as we have to compute it for several batches. And therefore, I investigated the recent weeks another approach, a graph-based approach, where we look again at this optimal pairwise distance matrix from which we also can build a complete graph. So each with the weight of the edges being the minimal pairwise distance in 3D velocity of those 2 stars. So each star is connected to each other star. And the goal is to build a sparse graph out of it, like to remove the edges that have unrealistic values. And in this sparse graph, we can then apply community detection and find like the clusters like this. And the criteria here is, for example, remove edges that have larger velocity differences than, for example, 5 kilometers per second, because those stars will not be part of the same cluster. And then we can apply community detection to find here nodes that are highly connected and that are like the true clusters. And if I did this, I could really recover almost all the cluster stars with an NMI of 0.95. But we also have, of course, a lot of background stars because it's only a clustering in the velocity space. You would need to additionally apply then your clustering in the velocity and the positions afterwards. And the advantage here is that we only need one hyperparameter like this fresh, and on this very however
Oh, me, sorry. I got it up there.
okay. Yeah, and this smaller data set is much more efficient than the deep learning approach. However, an issue is that we need to get rid of some magnitudes of order of edges to make it really a sparse graph. And it's not always, this one criteria does not always remove enough edges. So I'm currently working on finding additional criteria how to remove edges. Maybe one idea I'm currently working on is, for example, remove them also if one star of the pair of these stars have a large value in predicted radial velocity, optimal radial velocities, because it's also unreasonable. But yeah, this is like work in progress, and this is my overview. Yeah, like in this local solar neighborhood, we have to deal with projection effects that makes it hard to reliable density-based clustering. And we compute this minimal pairwise 3D velocity differences to get a constraint in the proximity, also in the velocity space. And then we tried up to now 2 different approaches, like a deep learning approach, where we can recover the cores, but it has still a large running time, and this graph-based approach can recover more cluster members, but it has like the potential for low running time, but I'm still in the method development stage because I just started my PhD. And yeah, I hope I will find a good solution. Thank you.
Question for Nora. I know this for Nora. I think it's welcome. So I do have one. So if I understand correctly, what you're going to do here is try to learn the 6D distribution of these parameters from the objects for which we have it, you know, including the radial velocity.
Yeah,
and try to see
constraint of the errors from it.
right, and then try to see if that's enough for you to cluster in even objects for which you don't have the radial velocity in a reasonable way. So you've tried this with simulated data at the moment. Is that way you've been testing this on? And if so, do you think you're recovering that structure with the sort of accuracy that you need in order for it to be applicable to real data?
Yeah, I aim to get like a perfectly.
Maybe use this just yeah.
I aim to get like a perfect clustering result on the simulated data. It will be, of course, worse on the real data than, so it should work perfectly on the simulated ones, and then I want to apply it on some parts of the real Gaia data where the nodes, for example, the clusters, and try, can I recover these known clusters with the method? And this would be a first like insight, it works actually pretty well or not. And yeah, but for now I'm just doing it on simulated data.
I wish you should consider back to back. Other questions, comments? No? Yes, Christine.
For your current simulated data, how are you, the dispersion and the just like, how are you going about simulating the clusters to then reconstruct? Like how, do you make any assumptions about like how dispersed they are over time or?
Yeah, like they're Gaussian distributed clusters, and I can just put like how much dispersed should they be in positions and velocities. And I looked at the known nearby moving groups, how are their positions, how dispersed are their positions. They're broadly span about 20 parsecs, so they're dispersed in the positions, but they're still compact in their velocities. Maybe not as perfectly as in my simulations, of course, and not Gaussian distributed, of course, but perfectly. It's an approximation.
So it is based on like real observation.
Yeah,
the other
of these moving groups that we know.
Yeah.
Is that it? If so, thank you, Nora. Thank you, Rishi. Thank you, both speakers, for nice update.